using the electrochemical potentials, we can derive the Nernst equation. However, we've got something a little bit extra here. That's not the Nernst equation. And this turns out to be a non-equilibrium potential. And that has to do with the fact that there exists now a potential difference between our two phases. And why would that be? Well, the main reason is that if we go back to the original equation or the original cell, notice the phase alpha and phase beta here, we've got this porous membrane. And so whenever we have a different type of solution on either side of a porous membrane, we have what they call a liquid junction. And whenever we have a liquid junction, as we've already mentioned, there's going to be a potential developed across that. And it's a non-equilibrium potential because at equilibrium, those two solutions would be mixed together. And we don't want those solutions to be mixed together. And so the potential for the cell reactants in general can be at equilibrium, but there will be an additional potential that's a non-equilibrium component of the cell, and that's due to the liquid junction potential. So even when we can derive a cell potential, sometimes things crop in, we get these extra potentials that we have to take into account. How am I doing? Okay. Well, let's explore quickly the idea of a liquid junction potential. Well, we're not going to really go into a great deal of discussion about it, but I want to explore the idea of it just a little bit for you guys. There really are three types of liquid junctions that we have to worry about when we're measuring cell potentials. And the most common type is the hardest to deal with theoretically. But let's talk about the three types. First type is called type 1, and it has to do with two phases, liquid solution phases, where the components in each side of the phases are the same, but are simply at different concentrations. So concentration in phase alpha, for example, is greater than the concentration in phase beta. In that case, because of diffusion, we'll get a transport across the membrane. But because the mobility of one ion is likely to be larger than the other, in this case the hydrogen ion has got much higher mobility, it's going to transport much more efficiently, and so we'll end up with a charge at the interface, that liquid junction effect. Now you can see why that's a non-equilibrium effect. If we let that diffusion occur to infinity, all of those species would be maintained, would be at the whatever the equilibrium potential would be. Now there would be no cell potential build up. But usually that, because the membrane is there to prevent that specifically from happening, we're always going to have a cell potential across that membrane. The second type is where we have one component of the electrolyte the same, but we'll have the other one will be different. For example, HCl on one side and potassium chloride on the other side. We'll get, depending on the type of species, we'll get transfer by diffusion across one membrane, for example, the hydrogen to the potassium side, and so would the potassium transfer back. And in this case, we've made it so that the concentration species in phase alpha is the same as the concentration phase beta. So the chloride ions are not going to migrate or diffuse because they're the same concentration on either side. But because the hydrogen ion mobility is higher than the potassium ion mobility, again we'll get a buildup of positive charge on the one side of the membrane. And so again, the liquid junction potential would look something like that, where we'd build up a potential. The third type of liquid junction potential is when it's not one of the other two. In other words, example would be hydrogen ions on one side, potassium ions on the other side, chloride ions on one side, say nitrate ions on the other side. And so it doesn't really matter what the concentrations are. In this case, we'll get a transference back and forth. And in this particular case, it will turn out that the chloride and the nitrate have approximately the same mobilities, whereas the hydrogen ion is still much more mobile than the potassium ion. So again, we would get a negative ion and a positive charge, or negative charge on one side and a positive charge on the other side. Now I've just stated here that the hydrogen ion has a higher mobility than the other species. That's borne out by experimental measurements like this, where they measure liquid junction potentials, which will give us that information. But you can actually calculate those things based on some physical properties of the ions as well. Well, an important thing to think about when we're talking about liquid junction potentials are things called transference numbers, which is the fraction of current carried by a particular ion. Remember that in any given electrochemical cell, the current that's carried through the cell has to be carried by the motion of ions. And so if we have a cell that contains only hydrogen ions and chloride ions, we can ask ourselves, is say, a current carried by the hydrogen ions moving, or is the current carried by the chloride ions moving? Well, both are going to be carrying the current, but you might expect that if the hydrogen ion can move more freely than the chloride ion, a larger fraction of the current will be carried by the hydrogen ion rather than by the chloride ion. And that's in fact true. The transference numbers have the abbreviation T sub I, where I would be a particular species. So for example, be T sub Cl minus or so on. Has units of centimeters squared per volt second. And it's basically a velocity over an electric field. Okay. So it turns out that what's important in giving us the magnitude of liquid junction potentials is the magnitude of the transference numbers in a particular system. Now, the transference numbers are not a unique number for each ion. It depends on the particular system. And the sum of all the transference numbers have to be equal to 1. So if we have lots of ions in solutions, the transference numbers for any particular ion might be quite small. But for example, if we have a HCl solution, the transference numbers for the hydrogen ion, and if we just have HCl in solution, transference numbers for the hydrogen ion is maybe 83%. Transference numbers for the chloride ion, approximately 17%. So it turns out because hydrogen ions are quite small and they're very mobile, they usually have very high transference numbers in solutions. So you can actually imagine that, for example, if we look back here at our type 1 liquid junction potentials, can you show that again, Rob? The type 1 liquid junction potentials, you can see where the hydrogen ions are moving much more rapidly. They're transferring much more of the current, and in that case, it also suggests that they're more mobile, and so you can see why they would build up a positive charge in this case. Now, a system like this, where we have, for example, maybe 1 molar HCl and 0.01 molar HCl, we're talking about liquid junction potentials that may exceed 30 millivolts or so because of that effect. Okay. Now you can actually measure liquid junction potentials quite simply, just simply by putting an electrode on either side of that membrane. And you can also calculate them, particularly type 1 junction potentials, liquid junction potentials can be calculated pretty exactly. The other types 2 and type 3 can be calculated with some assumptions built in. The book talks about calculating those. I'm not really going to worry about that. I do want to make you aware that they're present all the time, though. Let's just look at one particular cell, say a silver chloride electrode that is in a cell of hydrogen chloride on one side and potassium chloride on the other side. And so we're using our silver chloride with 2 electrodes. And we can just measure the difference in potential between the 2 silver wires to give us the liquid junction potential between this HCl solution and the KCl solution. And if we maintain the HCl solution at, say, 0.1 molar, and we vary the potassium chloride concentration from, say, 0.1 to 1.0 to 3.5 to saturated concentration of KCl, the junction potential, often abbreviated E sub j, goes from 27 millivolts to 8.4 millivolts to 1.1 millivolts to less than 1 millivolt. Why is that happening? Well, you see that as we make the KCl solution more concentrated, the junction potentials start to decrease dramatically. One of the reasons for that is that now, even though the hydrogen ion is much more mobile than the potassium ion, there's so much more potassium ion in the system that the difference in mobilities are negated. And the potassium and chloride ion now govern the mobility, govern the junction potential that we observe. The other reason we use potassium ions and chloride ions is that they have approximately equal transference numbers. So in this particular case, the transference of chloride ions across the interface is compensated almost exactly by an equally facile transfer of potassium ions across the interface. So potassium chloride is often used for these sorts of situations because of the unique characteristic of the potassium ion and chloride ions having nearly equal transference numbers. Okay. Well, just on that note, let's talk about 2 more things to do with solutions. One is the conductivity of the solution. All right, and just like anything, if we can think about what makes a solution more or less conductive, we can think about solutions having, are we done with the tape?
3 minutes.
I think we should be done. Why don't we stop the tape there then? How are we doing it? We can stop here for a minute and actually are we stopped now?